All right, everyone, Mr. Graham here. I'm here to introduce you to our next topic today, our next unit. This unit is going to be on what we call thermodynamics, and you might know by the name thermo, you might think heat, temperature, things like that, dynamics, motion, and so essentially thermodynamics is the study of how heat flows, how heat moves essentially from one object to another, or from one system of objects to another. And when we talk about thermodynamics, what we're really studying is what's going on the microscopic scale. Temperature itself is a measure of the kinetic energy of molecules and atoms. Even if I have a solid here, like this little block of metal, the atoms within this block of metal are constantly in motion. They're just not freely moving like they would be through a gas or a liquid. They're just vibrating back and forth, jiggling back and forth. And so you have tiny objects with mass that are in motion, so they have velocity. And so we know that an object with mass and velocity will have kinetic energy. And so that's really what we're studying when we're studying heat and temperature and how heat flows from one object to another. We're studying the kinetic energies of the associated objects. But then we zoom in to talk about it on the microscopic scale, but then we can zoom out and talk about those heat flows from a macroscopic standpoint. It's much easier to deal with than talking about the motions of trillions and trillions and trillions of little tiny atoms within an object. There are sophisticated ways and not so sophisticated ways of measuring things like heat and temperature on the macroscopic scale. But really what we're talking about when we're talking thermodynamics is what's going on in the very small scale. Okay. Before I get on to our real introduction, I do want to point something out. Something that you might not know. Up until this point in this class, we've been studying what we call Newtonian mechanics. We study Newton's law of universal gravitation, momentum, energy, even when we talk kinetic and potential energies. All these things are under the umbrella of what we call Newtonian mechanics. It turns out that in the early 1900s, a real smart guy, you might have heard of him, a real smart guy named Albert came along and did some work that essentially supplanted Newtonian mechanics and provided a better picture for reality, for our experience of reality. Usually when we think of Einstein, we think the old guy with the crazy white hair. But he actually looked like this when he was doing his most influential work. He was in his early 20s when he started making a name for himself and coming up with things like the theory of relativity, his explanation for the photoelectric effect, which is actually what he won his Nobel Prize for. So this is Einstein about the time when he was actually doing his most influential work. And the thing is that when he came out, you probably heard of relativity. Relativity actually says that Newtonian mechanics is not complete. It doesn't provide a complete picture of reality. And so Einstein came along, developed the theory of relativity, which explained everything that Newtonian mechanics explained, but then it also explained all the things that Newtonian mechanics cannot explain. Things like the weird orbit of Mercury because it's so close to the sun. Things like, well, I'm not going to get too far into it because Newtonian mechanics does work. When we sent when we sent the first people to the moon, well, every person to the moon. When we send satellites out to orbit around the Earth and send probes out to the outer reaches of the solar system, we actually use Newtonian mechanics because it works for the most part. It's only when you get to incredibly high speeds or incredibly high regions of gravitational pull, like around a black hole or really close to the sun. Give me 1 second, sorry. Had an alarm on my phone. Then Newtonian mechanics breaks down and it doesn't provide a clear picture of reality, where relativity does. And so this happens a lot in science. We come up with an idea, it explains certain things, but then you find things that it doesn't explain, and so they have to come up with other ideas. The reason that we study Newtonian mechanics, though, is because, again, it works in most cases, and because relativity is just really, really hard to understand until you have a firm knowledge of Newtonian mechanics. The reason I'm pointing this out is because, relativity supplanted Newtonian mechanics. You guys learn about the Bohr model of the atom, the different models of the atom, the early models of the atom, and then it wasn't until quantum mechanics that we had a real good understanding of what actually happens on the atomic scale. The Bohr model of the atom works, but just for the hydrogen molecule, the hydrogen atom. When you start getting to larger atoms, the Bohr model starts to break down, and so now we have our modern quantum mechanical view of the atom. And so science progresses like that. Ideas, theories get supplanted again by other better theories that are more descriptive. Here's a quote by Einstein, though, smart guy. Thermodynamics is the only physical theory of universal content concerning which I am convinced that, within the framework of the applicability of its basic concepts, it will never be overthrown. So Einstein, in studying thermodynamics, realized that, you know, my relativity took the place of Newtonian mechanics, but I'm pretty sure that this thermodynamics thing is never going to be overthrown because it provides such a good description of things like heat flow. And really, when it comes down to it, physical processes literally cannot happen without the flow of heat in some way, as we'll talk about as we go on in this unit. So, good quote by Einstein. He the guy that overthrew Newtonian mechanics, claimed, and to this day it has been borne out, that thermodynamics is probably never going to be overthrown by another better description of reality. So it's a nice little introduction to what we're going to be talking about here. Some key vocabulary that you'll want to know. Temperature. When we're talking thermodynamics and heat, we're usually talking about temperature. Temperature is actually the average kinetic energy of a system of objects. And usually when we say that, we're talking about the average kinetic energy of a bunch of atoms or molecules within a solid, liquid, or gas. In a gas or a liquid, the atoms are moving around, they're freely flowing, like the gas in this room. In a solid, they're locked into their structure, and they just kind of vibrate back and forth, like in this little block. So that's what we mean when we're talking about temperature. It's not actually kinetic energy, it's just kind of a measure of the average kinetic energy. It's kind of weird, but just understand that, you know, when I look at the thermostat and it says 71 degrees right now in this classroom, that's just telling me information about the average kinetic energy of the gas molecules within the room. When we're really talking about heat, what we're talking about is thermal energy. Thermal energy. And that is when we're talking about the actual kinetic energy of the objects as they vibrate or as they move. And we can call this the sum, and I'm going to put this in red, the sum of all energy within a system of objects. Energy within the system of objects. And again, usually when we say objects here in this context, we're talking about a bunch of small atoms or a bunch of small molecules. Okay. There are some misunderstandings that a lot of people have whenever they're first studying thermodynamics when it comes to things like thermal energy and temperature. And so I'm actually going to show a short Bill Nye clip to try to dispel those misconceptions before they actually, arise. Now, if I had any video editing ability or skill, I would splice this video in. But I don't have any video editing ability, so we're just going to watch it up here. I'm going to hold the microphone up to the speaker, and we're just going to watch a short Bill Nye clip.
The mountains are icy, but they've got motion of molecules. Ha! See, even cold things have heat. Things like snow and icy mountain lakes and glaciers. They've got heat. Anything with molecules has heat. It's just that the molecules in cold things are moving more slowly than the molecules in warm things. You with me? Okay, y'all ready? Sing along. It doesn't matter whether something feels cold or hot. If molecules are moving, it's something all things got. You know the words now, sing along. It doesn't matter whether something feels cold or hot. Here's a question. Which has more heat energy? This hot burning match or this beautiful ice sculpture of science? Well, the match is hot, right? Sculpture's cold. Well, they're both made of molecules, right? But which has more molecules? Well, the ice sculpture. A lot more molecules. So although they're much colder than the match, they actually have more heat energy. More molecules, more heat energy. Think of it this way. Suppose you tried to take a burning match and use it to melt the whole ice sculpture. Well, it's not going to happen, right? I mean, the match is going to run out of molecules long before the sculpture. So, more molecules, more heat energy. Ooh, ow, ow. Careful.
All right, that's what we wanted to hear. Again, sorry about my lack of video editing skills. Wish I had better video editing skills, but I just don't. So, sorry about that. I'm sorry about the cringy song. But it makes sense, or at least it's a good description. So the point there is that the lit match, obviously, higher temperature. Higher temperature, the average kinetic energy of each of the atoms within the match, the burning match, higher than the average kinetic energy of the atoms within the ice sculpture. But if you added up the total kinetic energy of all the atoms, because there's so many more atoms in the ice sculpture, then there's more kinetic energy overall. So there's actually more heat energy within a larger ice sculpture than there is within a burning match, which is kind of weird. Okay. So we have three different scales. Moving on, we have three different scales, temperature scales, that we use to measure with. We have the Fahrenheit, the Celsius, and the Kelvin. The Fahrenheit scale, it's the one that we're most used to. However, it's the least useful. So when you know it's 100 degrees outside, you know it's hot. You know that you don't want to wear a jacket. When you know it's 32 degrees outside, you know it's not hot. You know you want to put on a jacket. It's probably cold. The thing is that that's the Fahrenheit scale, right? 32 degrees is freezing. I even forget what boiling is, but it's not very useful. The degrees Celsius, it makes the math of thermodynamics a lot easier if we use degrees Celsius or Kelvin. Degrees Celsius is actually defined so that 0 is the freezing point of water at STP, standard temperature and pressure, and 100 degrees is the boiling point for water. And then they just put 99 divisions in between those two. So that's going to be your Celsius temperature scale. The Kelvin scale has the same increments. It increases at the same rate as the Celsius scale. So an increase of 1 degree Celsius is an increase in 1 Kelvin, but they start at different places. Kelvin actually starts at absolute 0. And absolute 0 is defined as the temperature at which all atomic motion would stop. All the jiggling of atoms within a solid would stop. All the objects within a gas would stop moving. All the molecules within a gas would just stop moving. It's actually pretty much considered to be impossible to reach. Scientists in the lab have reached 0 degree, within a billionth of a millionth of a degree of absolute 0, but they can't quite get to absolute 0 because it's thought to be impossible. So we're going to stick with these two. When we do the math, when we do our calorimetry, when we do our heat flow math, we use degrees Celsius or Kelvin. Okay. Something I want to point out is when we're talking about heat, and we're actually talking about, when we say heat, we're talking about really heat flow. From a physics standpoint, heat is heat flow, and it is the transfer of thermal energy. The transfer of thermal energy. And that transfer of thermal energy can go from goes from objects with high temperature to low temperature. If I have this hot plate here, which is very hot, and I put my hand on it, I'm going to get burned. The molecules in the hot plate are moving very fast. They're not moving like in a gas, but they're vibrating very, very quickly. So if I touch my hand to it, my hand is a much lower temperature than the hot plate. The atoms within the hot plate will make contact with my hand and then just jiggle them real, real fast and cause it to burn. Like that transfer of heat actually damages the atoms that make up my cells. Okay. Now, when we talk about heat flow, there's 3 ways. There's 3 ways that heat can flow from one object to another. The first is conduction. And what I just described is heat flow by conduction. You have to make physical contact, and then the atoms physically make collisions with other atoms within the other object, and they transfer their kinetic energy that way, and so the heat will flow from a hot object to a cold object. The second one is convection. And convection, if I have my tea kettle here, and I open it up, you see some steam coming out. I put my hand over it. I'm not making physical contact, but I can feel the heat coming up, and that's because of convection currents within the air, within the water as well. The convection, you heat up a substance, it becomes less dense because it expands, and then it rises. That happens with liquids and with air. and with solids over a long enough time. So yeah, that's heat transfer by convection. And then we have heat transfer by radiation. Radiation is electromagnetic radiation, not like the alpha radiation or the beta radiation that you learn about in chemistry. We're talking about electromagnetic radiation, light, but not just visible light. All wavelengths of light can transfer heat. When I put my hands to the hot plate to the side like this, I feel heat, but there's no convection currents going horizontally. They always go up. I'm not making physical contact, and so I'm not feeling the heat that is that due to physical contact. So I'm not feeling heat by convection or conduction. What I'm feeling is the radiation, mostly thermal radiation. And so heat can actually, the atoms, whenever they absorb the heat from the electrical outlet or they generate heat using the electrical energy, the molecules vibrate back and forth, and they actually emit wavelengths of light. Now, that light we can't see with our eyes. It's outside of the visible spectrum. That light is actually in the infrared, mostly in the infrared portion of the spectrum. If you've ever seen the Predator movies, the 1987 Predator movie with Arnold Schwarzenegger, great movie, by the way, great movie, but only watch it once you're 17 because it is rated R. But the Predator actually sees an infrared. And so when it flashes to the Predator's vision of the people, Arnold Schwarzenegger, he's hunting, you can actually see what infrared would look like if your eyes were sensitive to infrared. But that's what I'm feeling. I'm feeling mostly infrared radiation that's carrying the heat away from the atoms to the side. So I get all three types of heat transfer from that hot plate and from any fire. You'll feel all three types. Okay, so those are the three types of heat transfer. Moving on. Again, this is just a broad overview of thermodynamics, everything that we'll learn about in this unit. I just want to give you a brief intro. So we talked about the general. We got temperature, we got thermal energy. Thermal energy you can often equate with what we call internal energy, which I'll talk about in a second. But so we're dealing with a new subject here, thermodynamics. There are laws associated with thermodynamics. The first law that you typically learn about is weird because it's called the zeroth law. And it's really just the law that was instituted. It was mandated so that the other laws work. It's really easy to understand. It makes perfect sense. But mathematically it was needed in order to make sense of the other two laws. And so the zeroth law just says if I have three objects, which I will call object A, object B, and object C. The zeroth law says that if object A is in thermal equilibrium with object B, just meaning that they're the same temperature, and A is also in thermal equilibrium with object C, meaning those two are at the same temperature, then objects B and C must also be at the same temperature. That's it. It's real basic. If one thing is the same temperature as another, and it's also the same temperature as the third thing, then the second and the third thing have to be at the same temperature. Okay. Again, that was just... This is a descriptive law that was instituted in order to make the other two laws work at a more fundamental level. Okay. All right. Now the first law can actually be symbolized or can actually be expressed as an equation. And I like cars, and so I like thinking of cars when I'm learning about the first law or teaching the first law. Let's say you look at your car engine, big iron block with cylinders cut into it. So here's one cylinder. If you got a fast car, you got eight cylinders, six if you got like a souped up turbo. If you got a little 4-cylinder car, it's probably not very fast. So here's one of the cylinders. Now what happens in your car is you got a little piston that goes in the cylinder, and you put oil in your car so that as the piston moves up and down, it's lubricated. It doesn't generate too much heat because then that'll cause everything to break. And that piston is connected to a crankshaft, and as the piston goes up and down, it rotates the crankshaft. That rotation goes to the drivetrain and spins your tires. And you might have heard of fuel injectors. Fuel injectors actually put fuel in to the chamber here, into the cylinder, and it's contained by the piston. And that fuel, it's gaseous, by the way, when it goes in. The fuel injector takes the liquid gas, converts it to gaseous gas, and puts it in there. Then you have the spark plug. You have the spark plug that has a little arcing spark or electrical circuit that creates a little spark that actually ignites the gas. And when the gas ignites, the piston moves up. Okay. So from a thermodynamic standpoint, when you ignite the gas, you liberate that chemical energy, and it turns into heat energy. It gets hot. It's an explosion. It's literally an explosion. And so we say that that heat is plus Q, right? We have an interjection of heat into the system, and I don't know why they call it Q, but heat is the symbol in the equations for heat is Q. If heat's taken away, then it's negative Q. But here we're inputting heat, so we get a positive Q. And then what happens is that work is done, right? This is the before. If I look at the after picture for this, the piston has moved up because so here was the original position of the piston. Now it is moved up. And so that happens because the hot gas creates a pressure, which is equated with force, and that force pushes the piston up. When the piston moves up, work is done. Force, distance, that's work. And so you interject heat, and you get out work. But not only that, not only do you get work, you also heat up the surrounding engine. You might know car engines get hot when they're on. And that's because the atoms within the wall here start vibrating because of the heat. It's inescapable. You cannot avoid that. If you have this explosion within the piston, yes, you're going to push the piston up, but you're also going to heat up the surrounding walls. There's no way of bypassing the fact that the heat is also going to cause these molecules to move back and forth a little bit. And so the equation that describes the first law is just the heat put into a system or taken from a system will equal the work done by that system or done on that system plus what we call the change in internal energy. That change in internal energy is the increased kinetic energy associated with the increased temperature of the material involved in the process. Okay, so this is essentially the first law of thermodynamics. First law of thermodynamics says that if you put heat into a system, that system will be able to do some work. That's the whole basis behind internal combustion engines, also steam engines, also any type of engine. But then you're also going to get an increase in internal energy of the system, meaning it's going to heat up. And it's inescapable. There's no such thing as a 100% efficient engine. If you get 100 joules of energy, heat energy provided by the gas, you're not going to get 100 joules of work. It's physically impossible because you will cause an increase in internal energy of the surrounding material. Okay? So that's the first law. The second law is one, and really that Einstein quote at the beginning, really it's talking about the second law. The second law says that and I'm just going to write it, the entropy of the universe, can I spell universe? Always increases. And actually tends towards a maximum. It's asymptotically approaching a maximum. What is entropy? Entropy is a very abstract concept. It's very difficult to understand. Usually, I know I didn't understand entropy until quite a few years of studying physics at the university level. The analogy that they use to try to get the point across is that energy or entropy is associated with the disorder of a system. This is just an analogy. Please understand that. It is not actually the disorder of a system. It is an analogy for it. Or disorder is an analogy for the system. An easy way, if I take a ceramic coffee mug and I throw it at the ground, it's going to shatter and it's going to break into a bunch of pieces, and those pieces are going to be disordered. It's very unlikely that I'm going to throw my cup at the ground, it's going to shatter, and then they're all going to assemble back into the cup, right? It's theoretically possible, but it's never going to happen. And so we would say that the pieces scattered all over the floor are in a higher state of entropy than if they were combined together into a single object. Your room at home, if you don't clean it, your house when you're at home, if you don't clean it, it gets dirty, it gets disordered. And so you can think of, as time progresses, it gets more disordered, more dirty, and so the entropy of that system is increasing. So it's just an analogy. The actual concept of entropy is very statistical. It involves states and the number of ways that a certain state can be occupied by the molecules or atoms within it. But at the high school level, it's just fine to think of entropy as being a measure of the disorder of a system. And so I'm going to show a quick simulation to hopefully drive that point home. Let me zoom in here. And so this is a simulation of what's called a thermodynamic chamber. And let's say that I've established this system of particles, right? I put just this many particles here and just that many particles there, and they're in a very ordered state. I have these particles all in a very ordered state, and I hit play. I know this is blue and this is red, but everything's the same temperature here to start with. And so I hit play, and the atoms and molecules start bouncing around, and then eventually they become much more disordered than they were to start. And because of the statistical nature here, I expect always approximately the same number of particles here as I do here. Now I can, this is a misconception. Some people say, all right, well, if I understand disorder, then a universe tends to a state of disorder or a higher disorder or higher entropy. I can actually change that on a local level. At a local level, I can actually decrease entropy or decrease disorder, but I got to do work in order to do so. So I can try to turn this into a slightly more ordered state by heating up this side on the right. So I can increase that to say 2. So I'm essentially increasing the temperature of the red here. And then I can decrease the temperature over here on the right. And then over time, let's let it play a little bit. Over time, we now see, let me pause it, I've created a more ordered state. I've taken more molecules from here and put them here. Okay. Now if I take the average number of molecules here, it's going to be larger than it is here. But the only way to increase the order or to increase the amount of order or to decrease the entropy in a system, I must do work. I must put work into the system. And the process of doing that work, of generating the heat here, is elsewhere increasing entropy by an amount that's more than the entropy decrease within the system. So overall, the universe, the entropy of the universe will tend to increase, i.e. the state of disorder of the universe tends to increase. Okay. Again, please understand that that's just really an analogy. It's really just an analogy for what entropy is. If you want a true understanding of entropy, you gotta take some college physics and learn a little bit of statistics. Statistical mechanics, it's called. You got to learn that stuff in order to do that. Okay. And then I'm going to finish off with talking about how we can use thermodynamics to actually discuss how heat flows between, say, a hot plate and these. I got 2 different metals here. I got a chunk of copper and I got a chunk of zinc. And if I was to take these 2 objects and put them both on the hot plate, I'm not going to leave them on for very long or I'll burn myself, they'll actually heat up at different rates, right? I forgot which, I think specific heat of, I think the copper will heat up faster even if they're the same size. Actually, it seems like this. This might be aluminum. Yeah, this is getting hot very fast. This taking quite a bit longer to heat up. I'm going to stop there because they were getting hot pretty fast. So how can I track the heat flow from one object to another? Well, it turns out that whenever you heat an object, I just showed 2 different objects whose with the same input of heat from the same hot plate increase their temperature at different rates. And so how do we quantify how fast something heats up or how fast something cools down? Well, we talk about the specific heat capacity of a substance. In equations, it gets the symbol C, a large C, and if it's, usually we use water when we're trying to determine what the value of C is for certain objects. So you might put C for water, you might put C for copper, C for whatever substance you're dealing with. But the symbol is C, and it's essentially a measure of how fast an object will heat up when you put heat on it, or how fast an object will cool down when you take heat away from it. Okay. And we can relate the specific heat and the temperature change of an object and the heat that's either added or removed by what we call the calorimetry equation, or an equation that we use when we do what we call calorimetry. So when we do calorimetry, notice calorie is in there. Calorie is a unit of energy. And so when we're doing calorimetry, we're actually talking about how heat energy flows from one object to another. The equation is the heat will be equal to the mass of the object times the specific heat of the object times the change in temperature of the object. So if I put 10 joules of heat into a mass of, say, copper that's like 100 grams, then I multiply that mass times the specific heat of copper, which I don't know off the top of my head, but it's just a number, and times the change in internal temperature, the change in temperature of the object. That will tell me how much heat was put in. I can actually say if I put 10 joules of heat in, I know the mass, I know the specific heat, I can actually know before I do it exactly how much that object's temperature will increase. Metals, because they conduct heat very well, have very low specific heats, and so the lower the specific heat, the faster it will heat up. Something like water has a very high specific heat because it takes a long time. You know, if you put a pan on the stove and you turn on the fire, that pan's going to heat up real fast. You fill that pan with water, and it's going to take a lot longer for it to heat up, and that's because water has a much higher specific heat capacity than metals do. Okay, so this is a heat transfer equation, essentially. We will deal with this. There are experiments that we can use where we can heat up an object to a known temperature, drop it in a cup of water, measure the temperature change of the water, and actually determine what metal it is. You can actually identify metals using this process. When they put the calorie counts on the food that you eat, they actually do what's called bomb calorimetry, and they actually burn the food, measure the temperature changes involved, and then determine how much heat energy was actually liberated from the food, and so they can tell you exactly how many calories of energy are in that food. So that's quite a quick introduction to this unit. I just wanted to give you an overall idea of the things that we will be studying, but yeah, we'll obviously dig into all these concepts a lot more in the future in coming days. So yeah, hope you enjoyed.